In this clip, we're going to look at how to compute the average distance to the x-axis in a ball of radius a. All right, so my first take on this, what is the average distance to the x-axis? Well, distance to the x-axis, this looks like something, since we're in a ball, that would be great to set up in spherical coordinates, right? But then x-axis is the distance to the x-axis. That's something horrible in spherical coordinates, right? So maybe that's not the thing to do. But instead of shifting to a different coordinate type, instead let's just shift to a different axis, because the average distance to the x-axis is going to be the same as the average distance to the z-axis, just by symmetry, because it's a ball, right? It's a complete solid ball. There's no bits cut out or anything like that. It's the whole thing. So I'm going to just say, you know what? Let's just set up our coordinates by like rotating our head, and we're going to solve the problem for about the z-axis, and it'll have the same answer. And for the distance to the z-axis has a nice neat answer. It's just r. So that's rho sine phi. So it has a nice neat representation in terms of spherical coordinates. Okay, so it's going to be 1 over the volume, because again we're doing average, and then 0 to 2 pi, 0 to pi, 0 to a, and then we're just integrating the distance function. So that's going to be rho sine phi, the distance to z-axis, and then we've got rho squared sine phi from the Jacobian. So this is coming from r, this is coming from Jacobian, and then this is times, let's see, we've got d rho, d phi, d theta, and so once again, this is not a tricky integral to compute. Let's see, so we've got 3 over 2a cubed, canceling some pi's, and we get a pi over 2 from the middle one, and we get an 8 to the 4th over 4 from the last one. And so canceling off some business, we end up with 3 pi over 16 a as the average distance to your favorite axis.